come to my seminar. I'm very happy to be here, and I hope you can hear me all. Yeah, okay. So I try to share now my presentation, and yeah, what I aim to do now, maybe just a question, Glenn, how long am I allowed to speak?
So we should stop by 5 o'clock here in the Eastern United States and leave some time for questions. So you could go as long as 50 minutes, but I think it'd be better if you stopped it. It's usually a pretty talkative group. So I think if you left some time for questions, it will be filled.
Okay, I tried to limit it to 35 minutes or 40 minutes, something like that. Okay, great. Yes, as Glenn said, I will be at the Institute as the director for maybe 1.5 more years. And on October 15, Yanis Kokolis will follow me as the successor. So we will have an overlap of a little bit more than 1 year. And I'm very happy to have Yanis at the Institute. So also the collaboration with OSU will continue in that way. So today I would like to talk about two profile forming and tube forming processes. And this are basically contributions by my PhDs, Goran Krzancic, he did his PhD on the incremental profile forming process, and Christoph Becker, he worked on the superposed tube forming process, and Esmaili Nazari was also a PhD student, but he didn't finish his PhD. He was working on the incremental tube forming or superposed tube forming process with the Mandro and did a wonderful job. So I'm very sorry that he didn't finish his PhD. And Christian Löwe and Matthias Hermes are two of the very smart people we had in Dortmund, and they had very good ideas, and many of the processes developed at the institutes have been developed together with them. So I'm very thankful to them, as well as Daniel Staubda, who is now responsible in industrial company manufacturing material testing machines and making use of a lot of experience he collected at the institute. So two processes, one is incremental tube forming and one incremental profile forming. They sound very similar. By profiles, we mean structural elements which do not have circular cross sections, and by tubes, we may have circular cross sections, though they may vary over the axis. So I will start firstly with the, so I think you can see my mouse. I would like to start firstly with the incremental tube forming process and then switch to the incremental profile forming, which is also a topic on which we are cooperating with Gina and Satya at OSU. And I saw also Ian and Carter in the group who were also in Dortmund working on that process. So what are the possible applications for the forming process of tubes in the seating? Seating parts are, by the way, security parts, so they have to be designed for extreme security with very safe structures and high-strength materials in order to reduce the strength. So here you have several interesting parts which are used in the exhaust system, which is getting less and less, at least in Europe. You have several parts which are banded tubes. And then you have, of course, tubes which are with reduced cross sections over the axis and different thicknesses. So they are typical examples. You might have helix structures and helix structures which are banded and which have much larger frequencies as shown here. So, and if you look to the state of the art, I'm not going to cover the state of the art. I just want to show two processes which are very genius in my eyes. The first one is by Tosawa, from Japan and his co-worker, Ishikawa, they looked for bending processes which are superposed with a rolling process. And by that, they were able to reduce the bending moment, depending on the reduction in rolling, considerably by almost a factor 2. And by that way, they reduce also the spring back and were able to form other materials which are difficult to form, though they apply it only for aluminum in this study. Another study, also from Japan, from Nakamura, who usually works on tribology, had also a smart idea to do bending with and plug at the location where the bending is applied. So also superposing some stresses and reducing by that the bending moment and the spring back and allowing to bend higher strength materials. And that was our motivation. We wanted to bend very high strength materials, DP1000, DP1100, and even titanium at room temperature and other materials with the methods we had in hand without heating them. So that was our aim. And I skipped that slide. And the idea was to superpose stresses and to superpose the stresses by spinning rolls. So we have 3 spinning rolls by which we reduce the diameter very slightly by a few hundredths of millimeter. We can do it also more, but it's enough to do it by a few hundredths of millimeter, and then apply the bending moment and bend the part. And the hypothesis is that the bending moment reduces drastically by this superposition. There are 2 versions of the process, one without mandrel and the other one with mandrel, and that was the work of Esmail Nazari, and we were very much impressed that the one with the mandrel was even more effective than the other one. But I will basically show you results for the process without the mandrel. So here you see a video of the process. I will skip certain parts. Now here, those are the rollers. This is now slow motion. Here is the tube in the middle. And you have a slight reduction of the diameter. This is the bending tool. And if we move a little bit further, you see the tube is fed from the through the machine, and then touching the bending tool, and the bending tool is now bending the part while it is spun. And we can look a little bit further. This is another view of the process, and here another view. Nice thing is you can now turn. Oh, sorry. You can now turn the or rotate the tube and then bend it in different directions. You can also move the bending tool and have different bending planes during the process. So if you look to the result, here you see the bending moment as 100% for the classical bending without spinning. And this is the bending moment with spinning and plotted against the process speed. And the process speed is a number obtained from the rotational speed of the spinning rollers and the feeding speed and the diameter. So depending on the speed, you see that the bending moment required for bending at room temperature drops significantly. In fact, it drops by a factor 20 if you don't use the mandrel. And if you use the mandrel, it drops even. It's a complicated figure. Please just look to the red one and to this black one. If you have a thickness reduction of 0.3 millimeters by the mandrel, you can reduce the bending moment by a factor of 50 to 2% of the original. So it's an amazing reduction of the moment. And in order to demonstrate that this is true, we had some guests at our institute, Julian Allwood from Cambridge, Julius Green who was or is a theater producer in London's West End, and Karen Watts. She is the senior curator of the Royal Armours Museum in Leeds. And she was very much interested in the process and didn't believe that you can reduce the moments in that amount. So they visited me, and we had, maybe I can make it a little bit larger, we had a rope at the end of the tube, and this rope has been actuated by Karen as the process was spinning, and through that he was able to bend DP 1000 steel tube without using any effort. So that was a very impressive process and demonstration of how good plasticity works here. So the explanation of this phenomena is very simple. You can find it through plasticity descriptions. So we had a very simple model, and this simple model assumed a plane stress state and a strain state such that we had a spinning strain, which was given through the reduction of the diameter, which is shown here from D0 to D1, which was very, very little, as I said. And then the bending strain, and the biggest assumption here is we assume that the bending strain is equal or is the only axial strain. And then from volume constancy, we could compute easily the thickness strain. And with that experimental data we had here, where we looked for the longitudinal strain over the circumference of the tube, we could show that the assumption of axial strain is equal to the bending strain is relatively good, satisfied. It's not exactly satisfied, but we are at the lower end of the experimental data, so we were quite okay with that result. And then using the strain increment ratio, which is defined as the axial strain divided by the circumferential strain. So that's the amount of the spinning and reduction we have during the process, eta. We could find the stresses, and by the yield criterion by Mises, you can easily find the axial stress distribution, which is used to compute the moment, and the moment is given by this simple equation. So it's a very simple model, but it's purely based on elementary plasticity, and you can explain by that model the drop of the stresses. Here you see the drop of the stresses over the circumference with increasing reduction of the diameter, starting with 39 millimeters, so the initial diameter was 40. You see that the stresses get flatter. That means you have less bending moment in the system than without spinning. And this leads then to the reduction of the bending moment, analytically computed. And you see there's a discrepancy between the analytic model and the experiment, but still you could show with that model that there is a significant reduction of the bending moment, and this reduction increases with the process speed. So there should be some other parameter which were not considered in our model, because our model was simplifying the spinning process by a drawing process, which is of course a big simplification. And you see here,
if I may just inject a little bit, if you go back to the previous slide, while we have this, I was just wondering for the analytical model without spinning, with length.
Without spinning, you have 100%, and of course it's independent of the speed.
Right.
So the speed is
does it match with the experimental data?
Yeah, that's the experiment here. That's the experiment without spinning, and that's the experiment with spinning, this red one, and the green one is the model with spinning. So this is, of course, this shows the reduction of the bending moment, and but it doesn't fit very well to the model, to the experiments with spinning. That was expected because the model is very
So
simple.
the analytical model without spinning matches.
I mean, without spinning, the model is nearly 100% fitting.
Yeah, that just wanted.
I haven't shown that. I mean, that's some very standard process which is modeled by. If you have the right data, then there's nearly 100% coincidence. But that was the problem with spinning. So therefore, is that okay?
Yeah, definitely.
Okay. So we then said, okay, we assumed that we have a simple extrusion or a drawing case instead of a spinning, which is of course not the case. You see here, depending on the spinning intensity, which is defined by this eta value, the number of rolls n, the rotational speed u, and the feed speed and the width of the rolls. You have different overlaps of the rolls and hence a different physical process. And using this factor, we looked, oh, sorry, I have here, yeah. Using this factor, we looked to the experimental and analytical comparison of the data and just simply use a fetch factor to correct our equation. And we found that this relationship between the experimental and analytical moment is more or less linear. And then you can use such on the logarithmic scale, by the way, and then you can use such a fetch factor here, the spinning intensity with the fetch factor m. And for every material, you can determine a different m factor. And then if you do that, we end up with a very good prediction of the moments and could, by this way, design our process very easily. Okay, so if you reduce the bending moment, you reduce also the spring back. And you see that here impressively. This is the part without spinning, and this is the part with spinning, and there's a huge difference in spring back. And this one at the top is the one where you have large spring back, and here you have less spring back. And you can see that also in the data, depending on the radius of curvature, you have a huge reduction of the spring back from this red one without spinning to the black one or blue one with spinning. The black one is the model, and the blue one is the corresponding experimental result. We developed also a model for the spinning and bending with the mandrel. That was much easier. I'm just skipping that, and it was much easier because we did not need here the assumption about the strain state. The strain state was given through the thickness reduction of the tube by the mandrel, and hence we had a much easier solution, which was also much more accurate. And you see with that model, we could predict the spring back rather accurately in this case. So this was the incremental tube forming, which is in my eyes a nice application of plasticity, superposition of stresses, reduce the primary forming force, in this case the bending moment, and by that we were able to form at room temperature very tough materials, very high strength materials, difficult to form materials, including titanium, as I said, and even magnesium. So the next process is the incremental profile forming process. This is a little bit more different, and here the motivation was also different. The motivation here was to not to reduce the forces. The motivation was to have a flexible forming process. As you know, metal forming is, because of the high cost of the tools, only for large batch sizes. And the aim here was to have a process for small batch sizes, for prototyping, but especially small batch sizes. And we were inspired by the incremental sheet metal forming process. So the basic idea here is to use tools, different tools, which are incrementally forming the tube. The application which we have here are parts like that, which you find also in different positions or structural positions of the car or bicycle or other vehicles, which are quite complicated in their geometry along the axis. So they have variable cross-section, they have non-circular cross-sections and different side geometries as shown here or here, a very complicated part. So those are our target parts in our mind. And to solve or to manufacture such parts, there is a large group of processes in the literature, starting with hot extrusion, flexible roll forming, hydroforming, draw bending with split dies, rotary swaging, and spinning, which we just show in the previous application for the tubes. But all of those processes are not flexible enough. So we were looking for another solution, and this solution was to use those actuators. So we have radial actuators that can make a kinematic motion. That means they define the displacement, or they can define the form of the part, which we call form close forming. So with the kinematical forming, you can generate geometries like that. When with the form close forming, you can generate parts like that. Form close forming is much more accurate. This is less accurate. And in that way, we were able to have a procedure to form tubes in a very flexible way. Here is the machine. We have 6 radial actuators. They are like stylus type tools. And so 6 radial degrees of freedom. Here you see the tools once more. And then we have 1 degree of freedom of the rotation of the tube and 1 degree of freedom of the actual motion. So totally 8 degrees of freedom for this process. And here in the videos, you see 2 different applications. This is the radial application of the tools. 2 of the tool containers are empty, 3 of them are empty, 3 are used. In this case, we have 6 tools used at the same time. And here, basically, the form closed forming is performed. And you see, you can change the geometry of the part at any location of the tube in a very simple way. And you can rotate the tube as well, or the profile, and obtain some helical geometries as shown there. So that's the process in general. And with that process, we are able to produce with different degrees of freedom actuated. For instance, if you use the radial motion of one tool and the rotation of the profile, you can generate all those parts, which are shown here, starting with the star-shaped, triangular one, a gear design, up to a combined one at different locations of the axial part. Or if you use, in addition to those 2 degrees of freedom, the rotational degree of freedom, you can end up with helical structures as shown here with different features. And if you use the same system, you can also do some joining. So you can join, for instance, 2 different tubes that have different diameters, or you can join different materials, aluminum and steel, by using the different actuators of the system. So that's the basic idea which we have here. And the flexibility of the process is given, of course, and the increasing complexity of the geometry is ensured through the increase of the degrees of freedom which are included in the process. And here you see once more a typical group of parts which can be generated by this process. If we use only tubular initial workpieces, we can use also non-tubular ones, and two active tools, and symmetric tool positioning, and a single step forming. We can generate totally 108 different geometries, only with that few degrees of freedom. And you see those geometries plotted over the number of kinematical tool axes and number of form closed tool axes and the basic kinematics or degrees of freedom which we allow plotted on this axis. Here you can place 108 different cross sections by just this restricted number of tools and motions. So if you use the full potential, you will end up with thousands of different geometries, which is an extreme flexibility, which can be achieved with the same set of tools in the same measure. And an extension of this process is that we have also the possibility to make shapes internally. So using some deep drilling machine tools, we can also put our tools inside the tube and generate, as shown in the video here, shapes which are just actuated from the internal of the tube. And that's something which is very exciting. So you can end up with very interesting shapes, which increases the possibilities from those thousands of geometric shapes to maybe several folds more at the end of the process. So this process has the big advantage of flexibility, as I said, but at the same time, it has, of course, also the problem of accuracy. And I will come to this accuracy in a minute, like also the incremental sheet forming process, which suffers also from accuracy. And this will be discussed now in a minute. But before that, to obtain some idea about the accuracy, you need a prediction of the radial tool force. And for that, we had a very simple equation. As I said, simple equations help us very, very much to design the process quickly and to get the first process parameters. And here, with a very simple formula, where Kf is the flow stress in German terms, which is multiplied by simply the area here. If you know the flow stress, you can compute simply the radial force for any of the indentation processes. And I mean, there's a deviation of 21%, which is fine for the first design purpose of the process, and of course, not sufficient to determine the precision of the process. And this precision issue has brought us together with Gina and Satya. And we decided to work on the closed loop control of this process. And for that, now this is from paper, the control loop has changed significantly, so I'm not going to show that here. That's the one we had in the publication, where we have three cascaded control loops, the machine control loop, the process control loop, and the part-to-part control loop of the specimens. And the aim is here, beyond the part-to-part control loop, also to have an in-process control. And we are working on that by developing the process controller, which is basically developed by Gina, and the soft sensors, which are based on analytical modeling and some other type of modeling, which is basically developed by Satya. And in trying to solve this problem, what we have to handle here are the three challenges: the sensing. So we need to have an inline sensing during the process to ensure also the inline control of the process. And therefore, several students from Ohio State worked in Dortmund and have analyzed the sensing methodologies and options of this process, and found very nice results by which we can modify and improve them and implement them into the control system. Then we have to model the system with very quick models. Here you see the finite element models, which are very good in comparison to the experimental results, but you cannot use them. They take several hours. So we need very smart analytical or quick numerical methods, which we can apply here. And Satya is specialized on that, and I think he did a great job. And we are not finished, therefore I'm not showing you results for that, but we are able, hopefully soon, to have those methods to have a very quick computation of the position and forces and spring back of the problem. And the spring back is the third challenge we have in this whole control, closed loop control procedure. The spring back has an enormous effect on the accuracy, like in incremental sheet forming. And we have to compute this unloaded and loaded positions separately. And that's an extreme challenge, because suddenly you have elasticity in play, and beside the plasticity, and you have a complex geometry, which is three-dimensional, not symmetric, and all that stuff. So this is a huge challenge we are facing with. And with that, I would like to close my work, and I hope that we will have soon very nice results in the closed loop control part, beside the paper we already published with OSU together. And I hope that this process will be also very successful in industrial applications. And I would like to close with this, my seminar. Thank you very much for your attention, and I'm very much looking now for the discussion.
Thank you very much, Erman. Beautiful, beautiful talk, and very inspirational. I like the careful thinking, modeling, and machine building that all goes into that. Very, very nice. Let me stand back and open the floor for others for questions first. Hearing nothing immediately, please do put up your hand or put questions forward through the chat. Either way will work. And go ahead, Jane, and I'll let you.
I was trying to wait for the others to ask first, but since it's quite so, let me ask this one then. So again, very nice talk. Thank you as always. For industry-wise, I'm curious, particularly for the springback slide that you showed at the very end. I was curious about what industry needs are in terms of the springback, accuracy, and in terms of geometric accuracy. And when you do the control, what it would be your, the control strategy right there. Because I was also thinking about, because it's incremental, right? So, and the tube is actually very interesting, very challenging, because if you fix this end, also the other end could be also deformed. So what's your thought on that?
Yes, excellent question, Jane. Thank you. I mean, the accuracy depends, of course, on the application, but basically what we aim with this closed loop control is to sense at different locations the tube and we can sense it in one cross section. We can sense it also in the axial direction, and then use this data and feed the control system to make an estimation of the adjustment of the tools. So maybe Gina can say more to that. He is the designer of the system. Gina, would you like to say something to the control aspects?
Sure, Erman. So, John, for spring back, let's visualize. There are two types, of course. You could wait for the unloading of the part after forming of the tube, and you measure the unloaded part geometry. And of course, if you are also measuring the part geometry under load, then there is information there to infer spring back. It's not easy to recover the information. Furthermore, that computation of spring back can only affect the next tube because the current tube has already been formed. So that would be the provision for accommodating spring back in the part-to-part control loop or the outermost control loop in the figure that you see. So that's the strategy for accommodating spring back based on post-process measurement. But that's not enough, because what we would like to do is, could we get spring back while you're forming the current part? And that, if we can do that, that will allow us at least an opportunity to modify the current forming process of the current tube. And so the figures that you see, if you go back to the previous slide that you just showed, Erman.
Oh, sorry.
The other one, yes. These are basically measurements made after the part is completely unloaded. So this basically refers to the measurement of spring back after the current part has been formed and unloaded. But if you go back to the block diagram, Erman, if you can go back to the block diagram.
Yes, I have to work a little bit. Yeah, okay.
So the brown color shows the process control loop. And if I can ask Erman to sort of have the cursor start at the point that says loaded profile geometry, which is that is at the end of the process control loop. Is that something that you can? I don't see the cursor.
But don't you see my cursor?
No, at least I don't.
Oh, I'm sorry. I thought the cursor was visible.
Yeah, I see, Gina, so I think I got what you're saying, it's right there. No, yeah, it's right there.
There it is, I see it now.
Yeah.
So, may I complete that, because this is an additional way to infer spring back. So, imagine a simple profile forming process, an axial grooving. So you have an indentation that's held constant. The indenter position is held constant, and the tube is moved linearly so that there's a grooving formed. So if you can sense the contour, say along the longitude of the longitudinal direction of the tube, while the forming is going on, you will be sensing the geometry at the indenter, but also in previously formed sections of the tube, which should have information about the change in geometry due to reduction of stresses as you move away from the forming junction. So to be able to do this, we need to be able to sense the contour during forming, and we're able to do that. We have demonstrated that we're able to, based upon the work that some of our students have done in Tekkaya's lab. And so the information, we're able to get information that indicates how does the part geometry change because of the reduction in the stresses as you go further away from the indenting section. What we have yet to do is, given that we have that sensed information, how do we characterize spring back? How do we then quantitatively estimate spring back so that it can be used for purposes of control? We have, and that raises issues of how do you model the process in a simple enough way so that you can hope to extract information such as spring back while the forming is going on. That is something we are currently engaged in, but I guess what I want you to take away is that we are able to sense information by sensing the geometry of the tube while the forming is in process. And so that has information about spring back. So the information is there. How do we extract that information in a usable form is still an ongoing activity. Does that address any what you started asking?
Yeah. I think I got what you were saying in terms of this, block diagram. I think maybe David and Robert will ask a similar question, I guess, because these two are the control people. I was wondering is like exactly how would you control that? What's the algorithm for controlling, right? Is that it's a feed forward feedback combined ones, but maybe that might be the question coming up. So
that is much
so
further down the road, Jan.
That's
much farther down the road.
Okay.
We are in the process of, can we get the information? And and the answer is yes. Then the question is, how do you then recover information about spring back, the parameters that define spring back? We don't have an answer yet because that ties into questions of modeling in a simple enough form. So we don't have that. The following reasonably satisfactory answers to that, we will address the question of, well, how do you use this information to change the way the process is controlled? And in my thinking, that is a simpler issue than the issue of modeling the relatively complicated process with a computationally simple model. So we're really working on that modeling part right now.
Dave, why don't you add your question?
I think the previous answer answered most of my questions here, but I think where this is going is you're going to have wherever your sensor is located, that is not fully the spring back location. That's like as the spring back is releasing some, right?
Yes.
So you're getting some information there. But
Yes.
then because that's downstream of where the actuator is, you're going to have a time delay with that. I don't know what your thoughts are. It sounds like you're still formulating the control solution, so maybe you don't have an answer for that, but what are your initial thoughts on the time delay?
You're right. There is a time delay, but let's assume that you can sense very close to the indentation section. And that means that a time delay will be short. And so part of our effort was just to see, can we sense this deformed contour along the axis of the tube close to the indentation section and going back, to the extent that a line laser that we use gauges it. And the answer is yes, we can come pretty close to about 0.5 millimeter away from the indentation section. So our sensing capability is quite good, and that's what we've been working on in terms of the experimental part. But you're right, there will always be there is an issue of delay, but we'll have to look to the controls literature on accommodating time delays, etc. But as I said, our efforts currently are focused on, well, how do you extract parameters that define spring back based on a model? And so we're working on that right now.
Okay, and then your time delay will be, I think, known because you know your feed rate. That's more
yes.
than half your battle with time
That
delay.
is that is very useful. Absolutely.
If you know it, yeah. Okay.
Yeah, if you have a model, that's good. And if you know that the extent of the time delay, yes, that offers us significant opportunities.
Hey, Robert, I think your turn.
Yes, thank you. Thank you, Erman, first of all, for a very exciting presentation. I have two questions. The first one is about the sensing part. I think, I mean, being able to sense online in process, this is very impressive. I was wondering, can you talk a little bit about, what is the sensing principle that have used, for example, for this? It seems to me this is a displacement sensing by nature, right? And if you look at the tool displacement, or if you look at the cross-sectional contour, it's a dimensional sensing. And what is the sensing principle? Capacitive or any other means, proximity, or what do you use?
All right.
Yeah,
Go
okay.
ahead.
Gina, please go on. Please go on. You spent a lot of time on that.
Well, I think more than me, the students who worked on it this summer, for instance, have a lot of familiarity with the sensing. These are laser sensors, line lasers. They do sense dimension, and we've been essentially evaluating, can we sense the cross-sectional contour under load? And obviously, there are questions of not being able to access the complete cross-section, but we're able to access quite a bit of the cross-section. Because of the bulging, for instance, you can imagine that if you're pressing the indenter down, the cross-section that is bulging, and we can sense all that quite well. The other sensing that we refer to, and that touches upon the time delay issue that Dave Helsley brought up, is sensing the longitudinal, the deformation along the axial tube axis. So and these are commercial sensors made by an outfit called Micro Epsilon, quite compact. They use blue lasers, and we feel very positive about the use of these sensors in a production environment, for this particular production environment.
So basically, just to clarify, you sense not necessarily exactly at the intersection between the two, actuator.
You cannot do,
right, but a little bit away from it.
Yes,
okay.
You're right.
Okay, good. The next question is just on the control part. All these strategies. So how was the implementation done? Basically, you use classical control, PID, or you use some combination of that with some data-driven type of strategy. I just wanted to understand how the control is implemented.
Okay, the control has not been implemented. That is a to be done kind.
Okay.
That's the situation. But I'll share with you what we think we can do. We are looking at a model. This is cold forming, and so a non-linear model, but in terms of and the process delay is negligible. So any delays in the dynamics come from the actuation, and we will be able to characterize that. So we are looking at a nonlinear process, and we are, I want to say, completely optimistic, but we hope that we are looking at a modeling strategy that will give us a computationally tractable model. And what we're looking at, the procedure that Satya Sitaraman, my colleague, is primarily looking at, is a physics-informed neural network for modeling the deformation process. And if we are successful at getting a model of that type, we do have the opportunity. I think that there are the candidate I have in mind is a model-based process control, the MPC approach that we would attempt. Yes. So it is a nonlinear process. And so we are looking at that kind of approach, but we are very far from experimenting with that or implementing it in any form until we have a model that we have for computationally tractable model that we can use as a basis for control.
I see. Thank you very much. Answered all my questions. Thank you.
So maybe I can add one more point. I mean, that's very challenging what we aim to do. Therefore, I haven't shown everything because it's not ready and finished. But what we have also in mind, and that's the experience we have from other process where we had also some control on banding, is to consider the variability of the material properties because they will influence the accuracy and the whole process as well. And to take that into account, we plan also to make force measurements in the actuators. So by measuring the force and comparing it with the force we were expecting for a given material model or material data, we can estimate the scatter of the material properties and use them also in the control procedure. But that's the further step.
That's that. Thank you. Thank you, and Gina.
So we're almost at 5 o'clock here. Just one more quick question, maybe on just the development of the systems. It is very impressive to me that you've been able to build the sophisticated equipment and the control and all of that. And then in specific, the end actuators on those. What are, start with this very specific. What are the lubrication conditions? Do you have issues with galling? Can you do softer materials like aluminum, or do you end up doing surface damage? How do you control those issues? And then
yes.
more broadly, tell us how you went about building the impressive equipment and unique equipment that's required to do this.
Okay. Very tough question, Glenn. I mean, let me start with the building of the equipment, and then I will come to the friction issue. The equipment, what we do is first we do a very simple preliminary setup. For instance, the process, what's now shown on the slide, this process has been done in a lathe. So we use a simple lathe to test the process idea. And then as we saw it's working, we move to making a prototype out of this for this process. And for this prototype, we ask usually a funding agency in Germany. So in this case, let me check, I think it was 29. In that case, it was the European Union, which had a fund for realizing patents or innovative ideas. So we asked for that fund and got the funding and made the machine. If we look to the other machine here, that was done in a similar way. But then we found a company which just bought the license, get the license from us. That is the Transfluid company. You can see, I think, in the next slide, 13. That's the machine here on the right, the Transfluid company. So they manufacture those machines now on order. So you can order one if you wish. And they manufactured the first machine for us, and we continued with that machine for our fundamental research. So those are the possibilities. But basically, we start with our own lab, with our own opportunities we have at the lab, and then make a very simple preliminary test, and then ask for funding to make an intermediate testing machine, and then end up by a company who produces commercially the machines, and then get maybe the first product and use it for further investigations.
I kind of knew that. I wanted to bring that out as a roadmap for all of our investigators here too. It's a good, you don't see that.
Yeah,
too.
I hope that answers your question. But I mean, you need a lab to do that for the very first test systems, a lab which is flexible and big enough to have the opportunities. And then you need those funding agencies that just give the money for innovative ideas to realize them and to make the first prototype. And then the rest, you need companies who are interested in good ideas and buy the licenses and make the money. I mean, we didn't make money by selling the license of that patent for this process. For us, it was more interesting to have seen that the industry is interested in the process and is using that. So that was the first part of your question. The second part about friction, we usually start with aluminum because the machines we have at the beginning are not strong machines, so we cannot test high-strength materials for this case. Now, for the other case, it was different, but for this case, so we started with aluminum, and there, of course, you have problems like galling and other tribological issues. We can solve them by using some sort of stylus with a rotating ball, so that you can reduce the relative motion and hence the friction. Or you use some sort of coating on the tools, or not on the tools, on the workpieces, which is used, for instance, in cold forging, or you use lubricants. But frankly speaking, those are steps we do at a very far development phase, because we are basically interested in the mechanics and seeing whether we can form the parts, and then think about the surface finish and the tribological issues. But in this process, you might have those issues, but there are solutions for that, which we also tested occasionally.
Good. Good. Anything else terribly urgent? Hearing nothing. Well, thank you, Erman, so much. Thank you, China, for color commentary. It was wonderful. What a perfect kind of talk for us. Yeah, lots for us to think about, and yeah, we appreciate that. And hopefully, you can get some nice sleep now. So,
thank you. Thank you very much for inviting me and for the excellent questions. Thank you.
Thanks.
Thank you.
Bye all.
Bye-bye.
Bye.
Bye.
So, bye-bye.
Okay, take care. Bye.